Hello. I am Yufeng Cheng, an associate professor from Southwest Jiaotong University. It's my great honor to make a brief presentation on our recent work on Metasurface-Covered planar Endfire antenna with vertical polarization. I will present this work from the following 4 parts. In terms of the background, it is well known that vertically polarized waves suffer lower attenuation loss than horizontal waves generally. Therefore, vertically polarized Endfire antennas have received considerable attention. In the literature, several solutions have been reported for designs of vertically polarized Endfire antennas. On the other hand, trapped surface waves are recently studied and utilized to design Endfire antennas. In part 2, let's start with a conventional magnetic dipole. The conventional magnetic dipole has a width larger than half wavelength in principle. To reduce the aperture, it is required to increase the longitudinal phase constant. Actually, by enlarging the relative dielectric constant, the longitudinal phase constant will be decreased. Therefore, as shown in the bottom left figure, metasurface is used as the superstrate. The width is dramatically reduced to less than half wavelength. Based on the above analysis, an initial VP Endfire antenna is designed. Waves excited by these dipoles are trapped within the metasurface and generate effective magnetic currents on the vertical plate. This slice gives the simulated E-field distributions in the XXII plane and the H-field on the left vertical plate. Obviously, trapped waves are excited by the right parasitic dipole and thus generate the Endfire radiation. According to the E-field symmetry, the antenna profile can be reduced by half. In addition, magnetic dipoles can form a linear array. That is the antenna evolution. The right figures show the reflection and radiation performance of these antennas. Some parametric studies are addressed and their results are shown. These studies help to explain the bandwidth enhancement by the resonant condition of trapped waves within a metasurface. The final antenna is fabricated and measured. According to the measured results, the designed antenna can operate from 4.2 to 5.5 GHz and has a peak realized gain of 9.9 dB. Finally, here are some conclusions. A novel trapped wave-based solution to design VP Endfire antennas with compact physical aperture is proposed. The antenna can be used for some wireless communication systems on or near the ground plane, such as the car roof-mounted terminal for vehicle-to-roadside unit/base station communication. Many thanks for your watching.
This video is used to introduce broadband, low-profile, planar reflectarray antenna based on an achromatic metasurface. An antenna design method based on the achromatic principle is proposed. The conventional reflectarray cannot effectively focus all the electromagnetic waves within the wide bandwidth, while the achromatic metasurface can achieve this, thereby broadening its working bandwidth. The traditional single-layer unit cell can only compensate for the phase distribution at the center frequency. Changing the thickness can adjust its working frequency point. The corresponding equivalent circuit can verify this performance. Different from traditional elements, the achromatic metasurface lens not only requires to correct the phase, but also requires to control the group delay and the group delay dispersion. For this reason, a 3-layer achromatic element structure is designed, and the equivalent circuit diagram of the multi-layer structure is presented. The 6 unit cells chosen are shown in the figure on the right. The abundant wideband impedance enables these pre-designed unit cells to generate more resonances than the conventional single-layer unit cells, which shows that these unit cells have more group delay and group delay dispersion, thus significantly improving the phase dispersion manipulation capability of the reflective metasurface. By adjusting the parameters of the 6 types of units, 228 units of phase and amplitude data are obtained. Then, genetic algorithm is used to select the units. Different from the conventional discrete multi-frequency point optimization, thanks to the wide band phase response of the units, the quasi-continuous frequency optimization method can be effectively applied. Finally, the array distribution shown in the upper right corner is obtained, comparing the theoretical and simulated amplitude and phase relationships at different frequency points. It can be found that the antenna has very good focusing characteristics in a wide frequency band. The fabricated sample is shown in the upper left corner. The measurement and simulation results of the sample are very consistent. The maximum gain is 25 dBi, the 3 dB bandwidth was 58%, and the maximum aperture efficiency was more than 40%. In addition, the radiation pattern within the frequency band was also very consistent with the simulation value, which verified the effectiveness of this design. In summary, in this work we designed and established an achromatic unit database, combined with optimization algorithms, quickly realized the design of wideband achromatic reflectarray antenna, which achieved 58% of the working bandwidth. This paper provides a complete set of design schemes for achromatic wideband reflectarray antennas, which can bring new ideas for the design of wideband antennas.
In this video, we briefly introduced the circularly polarized polarization conversion Metasurface-Inspired antenna array with low RCS over a wide band. The relevant work can be found in IEEE transactions on antennas and propagation. Antennas play a crucial role as communication devices for low observation platforms. However, the RCS of such platforms is severely impacted by the strong scattering of the antennas. One solution is to load metasurfaces around the antenna to reduce its RCS, but this increases the size and height of the antenna. Besides, antenna units with large dimensions are not suitable for array applications. This study proposes a co-structure design of the polarization conversion metasurface and antenna. The design involves 3 steps. Firstly, a conventional polarization conversion metasurface named Unit 1 is designed. Secondly, a feed structure is added to the Unit 1. Finally, a shorting pin is employed to connect the upper metal and ground. The shorting pin enhances the surface current density, leading to a decreased input impedance of the antenna unit. Thus, by adding a feeding pin and a shorting pin to the metasurface unit, a linearly polarized antenna unit is successfully designed. The reflection characteristics of metasurface units are simulated to verify the design. Unit 1 can rotate the polarization of energy in a wide band, while Unit 2 performs worse, particularly in the frequency range of 7.6 to 11 GHz. However, the proposed unit has almost the same performance as Unit 1. Therefore, by introducing a shorting pin, the polarization conversion metasurface unit can be directly used as the antenna radiator. The metasurface antenna units and their mirror units can form a circularly polarized antenna array. The units are arranged in a 4x4 array with a checkerboard configuration. A power divider using sequential rotation technique is loaded at the bottom. The Metasurface-Inspired antenna array is fabricated and measured. The results show that it has broadband impedance and axial ratio characteristics. In addition, due to the phase cancellation between the adjacent metasurface units, the scattering pattern is deflected in 4 directions. The monostatic RCS of the array is reduced by 10 dB from 7.6 to 16.2 GHz. More details of the work can be found in the reference. Thank you for your attention.